Thank you and welcome to this next talk, which I'm going to give on the historical data scientists. You know them by the names Tycho Brahe and Johannes Kepler. They were both astronomists or astrophysicists. And this couple in particular has a very reason to be mentioned in this context. They are more or less the first systematic scientists in this field of research. And they have a very peculiar way to achieving their goals, which I hope you will find interesting. To start off on this talk, I'm going to show you this very particular nose. Yes, it is actually a nose. It's a nose made of bronze, and it is perhaps the most famous nose from the 1400s and 1600s. So it's the nose of Tycho Brahe. He was most likely a very well-off little boy. He was born in the noble families. He had everything he wanted, and apparently everything he didn't have and desired, he would ask for it. This led him into this awful duel in which he was actually deprived of his nose. So it was cut off in a sword duel. Then he had this replacement nose to keep using for the rest of his adult life. So we're going to continue sticking with this man, Tycho Brahe, and we're going to also talk about his eccentricities. He was foremost a very fond friend of the king in Denmark. He lived in Denmark in the end of the 1500s years, and he was actually given his own island. So none of the other castles or mansions suitable for the man of his standard was interesting to him. And the reason for this, that he'd been given education from his young years. So he was educated as an astronomer. And being an astronomer, he would like to spend his time doing research. And this is also why we want to learn about him. Okay, so he built this castle, Uranienborg, which is on the island Ven. It's just in between Sweden and Denmark, and currently it's Swedish territory. So he built this to have his house, to have his staff, and to have his research. So inside this building, he had all these different instruments. His goal was to observe the positions of the stars and to do that more precisely than anyone had done before. The tools you would do that with at the time was quadrants and sextants and octants. So the ones you probably know from navigation at sea in the old days. Only thing that he wanted to be able to read the angles of the objects even more precise, so he built them bigger. So this is one sketch of one of these huge instruments he built. Still, there's challenges. If you have observatories where there's people, you have motion and vibrations, and you have steam, and you have light in times you might want none of them. So eventually he preferred to move his observations into Stjerneborg, which is his own and perhaps the very first observatory in astronomy of its sort. So in these buildings, he had a cellar, and all the instruments were put on solid base rock. And these quadrants and sextants was used to measure the angles. Now, he had a very special interest in measuring the positions. He knew from before there was no one who'd done this earlier. And he was a meticulous person, and he was a practical person. He could see solutions with existing tools and make them better. Now, as you probably understand, this is kind of going into the astronomy and the science we have today. Okay, so he wanted to do these observations, and after going on for a while, he actually made one very important observation for the time. And just to give you a reminder of the time, so he was born like mid 1500s and he died 1601. The Earth was established to be round, so Columbus was finished with his travels, but there was no possibility to kind of say how far away are the objects in the sky. Not at all possible for them to say that these objects we know as planets practically was the same as our own home. So none of this was established. Okay, so we lived at the time, or humanity lived at the time, believing the universe is something completely different. It's static, it's divine, it's made by the gods, it's perfect in every sense, and it's made out of other elements than the earth. Then suddenly this little thing appeared. Now we call this a supernova remnant. But in the year of 1572, it was a supernova. So that means an exploding star. This star was invisible until that day or that year where Tycho Brahe observed it. And it gave him a very solid reminder that the universe is not static. It is actually changing. Okay, so with this experience, he continued his research and he started making what was to be the most detailed and the most precise catalog of star positions ever made. Now, there's a lot of achievements done by Tycho Brahe that we should give him credit for, and he was a lot more than just the astronomer. But this story is about the work that led to the law describing the planet's motions and the scientific story. So this is kind of the main legacy which he's known for now. Still, he was under the impression that the Earth was in the middle of the universe, a so-called geocentric image of our solar system and the universe in general. So this was an old idea, and even though Copernicus, he was actually lived long ago, and he knew about Copernicus's ideas, Copernicus wasn't successful in giving more precise predictions as to when the various astronomical events happen. So, having not been convinced by Copernicus' ideas still, he wanted to suggest his own system or image of the solar system, in which you have your Earth in the middle, the moon orbiting the Earth, and just outside the orbit of the Earth, the sun. And then again, around the sun, you have Mercury, Venus, Mars, Jupiter, and the other planets. And outside of those, again, the stars. So this was the idea that they had at the time, and also a very necessary part of it is the so-called epicycles, first introduced by Ptolemaios. So this was in order to explain an anomaly in the orbit of the planet Mars, which has something called a retrograde motion from time to time, approximately every second year. The planet Mars stops going from the east to the west on our sky and goes for a short while eastwards before returning in going towards the west. So they kept this idea about the epicycles. This was, as we know now, this was kind of the big problem with the current view of how space worked. Okay, so still he had this convince, and then at the later parts of his life, he turned, or the new king of Denmark, turned not so happy about it. What really happened was that the new king, the son of the king that Tycho Brahe was a very fond friend of, took over, and this son did not like Tycho Brahe. He deprived him of all his goods, and eventually Tycho Brahe had to leave Ven and Denmark. Now, for the sake of the astrophysicists, this was a very good move to make, because after moving, Tycho Brahe brought all his tools for making the observations. He brought all his catalogs, which yet had to be published, and he moved to Prague. So this was in the year of 1599, where he get to know this young man called Johannes Kepler. Now, Tycho Brahe was the practical observer. Johannes Kepler was the theoretician and the mathematician. So he was able to see things and see solutions that Tycho Brahe had not. The main contribution of Johannes Kepler was then this, is his calculations, in which he was able to work with Tycho Brahe's data. But there was a problem. And the problem in its sense stems back from Archimedes' times. And we all know a very famous quote, "Do not disturb my circles." The idea of our space surrounding us was at the time that it was something divine, it was something perfect. And a perfect space must contain planets that are perfectly circular and follow perfectly circular orbits, simply because the circle is, in a way you can call, a perfect geometric shape. So none of them, until that point, would ever try to actually challenge the idea that the planets follow any other orbit than a circle. So Johannes Kepler, even though he wanted to go into the material, the observational material of Tycho Brahe, he was in a way not able to. Tycho Brahe and Kepler had a very complex relationship. They did not trust each other, and all until the death of Tycho Brahe, Kepler was not allowed full access to the archive. Still, on the deathbed of Tycho Brahe, he hoped that his life and his work was not in vain, and he left a note to Kepler telling him, focus on the orbit of Mars, the one planet which had the retrograde motions from time to time. Okay, so this was Kepler's mission, and on his way he stumbled upon this geometrical shape called an ellipse. Now, this ellipse might look circular to you, but it is not. It is actually elongated in the horizontal direction. Now, the special part about ellipses is that they have what we call two focal points. The circle has one, which is what we call the origo, or the center of the circle, while the ellipse has two. You can derive a circle from the ellipse, so it's not untrue that a planet can be in a circular orbit, but it is not likely. So this was the mathematical idea, and after working with the material, after looking into Tycho Brahe's observations, he found what is now known as the Keplers laws of motion, of planetary motion. Now, in this drawing, you can see an ellipse, which is elongated in the vertical plane. It is outside, no, sorry, it's placed inside of a circle to compare. And we have marked several triangles. Now, all these triangles are used as reference points to measure what we call the sum of the radiuses in the ellipse. And in the end, those are the lines you use to actually describe what shape of the ellipse should it have, should it be. There's another thing coming out of this, and that is you can, in a way, draw triangles that make out an area. So if you assume there's an object following the ellipse and you measure how large area would a line that sweeps from the origo of the ellipse out to the object and sweeps in the direction of the object's motion, how large an area would that cover in a set of time? And Kepler's discovery was that this area is the same regardless of where the planet is in its orbit. So this leads us to the Keplers laws, and this is the Kepler's third law, in which it's shown it's a relationship between the velocity the planet or any other object have and the period, the time it takes for that object to travel around the star or any other gravitational body. Luckily enough for Kepler, he also was able to discover a supernova. So his mentor Tycho Brahe did, and he also did. So this is now the supernova remnant of Kepler's supernova. Now, this wasn't the main point of my story. The next one is. So in 2 publications, Kepler presented for the world his findings. And his findings was in a large extent from both his work and Tycho Brahe's work. Tycho Brahe did not have time to actually publish his material to the full extent that he should have. So it was not known to the world the full extent of their common discovery. But at least this, the Astronomia Nova, was published in 1609, and in this Kepler presents his first 2 laws, 2 of 3. A few years later, in 1627, which is actually wrong with respect to the number in the presentation, it says 1609, but it is 1627. Kepler publishes his third law, which is the one you just saw in equation form. And he did something very great. He published the full tables of Tycho Brahe of 777 stars. There were actually 1,005 stars in that collection because Kepler himself had continuing doing observations after Tycho Brahe's death, and he had added 238 stars to the list. This point marks, in a way, the start of a new era in science. So nowadays, we talk about big data science or being a data scientist very often. The term itself, big data or data scientist, isn't new. It's become more known, and it's become known in parts of the society where it has not been known from before. But the term in itself works perfectly fine with the work done by Tycho Brahe and by Kepler. So how did they work with big data in the old time. They did not have AI. They did not have computers. They had pen and paper. Now, I'm going to be careful in this group, as probably several of you are very skillful AI and data scientists. I have looked into your field of research and I've looked into your tools, and I've noticed something very peculiar. What's common in any of these cases, if it's your big data you're going to analyze, or it's Kepler's big data or Tycho Brahe's catalog of stars, the most important thing is the question. You need to phrase the question as to what do you want from these data. If you do not have that question, you will never find a solution. It might be obvious, but it seems still a very fundamental restriction to the field of data science. After that, you need to describe your methods. You need to agree with yourself the tools for which you want to use to try to answer your question. And even more frustrating, you must try to guess the answer, or at least predict your desired answer. Perhaps not in detail. There is a question there, or there is an element of your question which you will never be able to answer. This is why you're doing your analysis. But still, in your choice of method, you need to have some assumptions as to how shall I proceed to get the type of answer I'm looking for. And to go through with this, the foremost qualities in you, the data scientist, and in Tycho Brahe and in Kepler is patience and resilience. For in the end, even though we do have computers now that do fantastic work, and I'm quite sure Tycho Brahe and Kepler would be envious of your tools today, you're getting nowhere unless you're managing the data correctly and asking the right questions to start off with, just as we've seen several good presentations of today. So in a sense, you could say all sciences, not just Tycho Brahe and Kepler's, but all sciences, they work at some point with big data. It kind of lies in the nature of science. You want confirmation. You cannot just have one conclusion. You need 10 conclusions saying the same thing. If they don't, you don't trust the result of the first conclusion. Of course, astronomy and astrophysics are no exceptions to this rule. And in terms of kilometers and numbers, I guess astronomy and astrophysics still have the biggest data. Still. I want to give you a challenge, an idea for something that you can bring on in your work and your hobbies. There is an ongoing search for black holes. These are two images in which there is a black hole in both of them, but the black hole is only visible in the left. Now, this might be obvious to what you expected, but black holes, they are black. So on the black background of space, they are invisible. You cannot see them, even with the best AI computer. But when a black hole comes in front of the light from another star, which is far behind, it's a micro-lensing effect, they call it. So it can actually enhance the light of that star a short period. So mind you, there's been astrophysicists who's systematically gone through several hundreds of images of a starry background, like the ones we see here. It is as if they're just looking for the needle in the haystack. They're looking for thousands of images of white dots on a black background, and they're looking if one of them has brightened at some point. And if it brightens, they might have discovered a supernova. That would be equally interesting. But once it brightens, they will continue monitoring that star, measuring its light curve, measuring how light changes through time. And if it has the right shape, the light curve, they found a black hole. Now, this is a job for AI, I'm sure, and there are scientists already working on this, how to implement AI and other new methods to find these efficiently. But maybe you have an idea. And so I give you the challenge. What big data methods do you know that could start the next revolution in astrophysics? I'm sure if you look around, there are some astrophysicists in your office amongst your colleagues. You will find them and you can start discussing this new future project. Thank you very much for your time. Thank you for listening and watching, and I hope you still have an excellent conference today.